I would like to talk about how to replace TSN, how to replace CAN with TSN. So my name is Kilian Brunner. I'm working at the ZHW in the team of Communication Network Engineering, and I'm also lecturing these topics in the bachelor. I want to take you today to a story of a customer who came to us with a real issue on his sensors, and I want to show you how we solved this with Zephyr. And I will also show you it was not always very easy. So not always straightforward. Sometimes you have to dig a little bit deeper to solve the problems in a way that it really fits. So this customer came to us and he told us, hey, I have a system. It is working. It is working with CAN. I have some limited bandwidth. Everything is customized for us. It's working, but it's all bare metal and it's very, very difficult to maintain. He already had the idea to go maybe to Ethernet, and he told us he wants to have more bandwidth. He wants to have standardized communication models. Of course, he also would like to have it all Zephyr-based, and most important, it should be easier to maintain as the today's system. So when we try to bring these two worlds together, from one side, we have the CAN, a traditional field bus, and the Ethernet on the other side. So first, let's have a look on CAN. CAN is designed for harsh environments. You can go on very long cables with single twisted pair cables up more than 1 kilometer. It's usually tailored to an application. CAN is designed for sensors. So usually you have very small packets where you can send data values. And also it's usually very low power, and therefore it's perfectly designed for embedded controllers. And usually you even have a CAN controller in the smallest ST controllers you find on the market. On the other side, we have the Ethernet world. Ethernet provides usually very high data rates. You have full duplex communication. You have this sub-microseconds time synchronization, which is maybe very handy if you build a sensor application, because then you can map all your sensor values to a very exact time. So imagine you have a distributed system, distributed over maybe a square kilometer, and you can measure, or you can point every measurement point to an exactly point in time. Then you can correlate the data much better, and you have much more information about that. Then with Ethernet, we have the standardized IP communication. We even have power over Ethernet, so we don't need extra wires. We have the economy of scales, but on the drawback, we usually have big connectors and very thick wires in comparison to CAN. Now, since some years, there are new Ethernet standards out here. One of them is 10BASE-T1L. 10BASE-T1L is, I would say, a mix between these. So we don't have very high data rates, but much more than CAN. So we have 10 megabit. It works on harsh environments. I can go up to 1.5 kilometer. I can use my loved time synchronization. I have cyclic data transmission, and I also have this power over the data lines. So again, in a nutshell, 10BASE-T1L tries to combine the best of these two worlds in a good way. So we have the higher data rates from the Ethernet world. We have the long copper runs and the harsh environment from the field bus world. We have IT communication from Ethernet, but we still have kind of low power and embedded. So I now try to bring these into some numbers that you have something to take home maybe. So the limitation of CAN. It's better now? So on a very small system, like maybe in a race car, we heard before, you have one server and 4 sensors. then you can communicate with up to 1 megabit. If you have now a bigger system, maybe 500 meter, 1000 meter distance, then your bandwidth is much lower, maybe 50 kilobit. So when we have the idea now of 10 base T1L, we just place some Ethernet switches, build a small daisy chain, and we have 10 megabit on a small system and also 10 megabit on a big system. I think this is very nice because you don't have to distinguish between small systems and big systems. You just have Ethernet and always the same performance. The next limitation is packets per sensor per second. We also heard that before in the Formula Student. So they may want to get a sensor value every 1 millisecond. So that means 1000 packets per sensor per second. So when we go back to the numbers from before, with CAN, the 50 kilobit and the 1 megabit, we see we have in maximum 350 packets per second or 7000 packets per second. Of course, some may say we use CAN FD, so we can increase it a little bit, but it's not so much. So basically, we do have these numbers. So if we now put these numbers into these different systems, we see on the small system, we get maybe our 1000 packets per sensor per second. On the bigger, we don't. If we bring in here also Ethernet, add the switches, and know that on Ethernet, the smallest packet is 64 byte. If we add or subtract the destination addresses, frame checksum, and so on, we get 64 byte of data, which is much more than in the CAN example. And we see we almost have 15,000 packets per second. So this leads to much more packets per sensor. So also here we have at least one advantage. Now, how would a sensor cell in such a daisy chain look like? The simplest way is drawn here. We have a host processor, we have a switch chip, and an interface in between. So on the host system, we would like to have Zephyr. We would like to have a sensor application that may speak with SPI, with an ADC or whatever. We have a time synchronization application, and we have some communication sockets. On the lower side, we'd like to have a switch chip that is offloading my packets, so data that is coming from the server can go through the switch chip without interfering with our CPU. And we would like to have a simple standardized interface, SPI. So when we're looking for a chip like this, we only find the 182111. This is exactly a chip designed for that. So we have integrated PHYs, we have an integrated switch, and we have an SPI interface to our host. And luckily, this chip is already supported by Zephyr. So when we look into the current driver capabilities, I draw it here. And you see the first change between the drawing before is we now have 2 host ports. We don't have a single switch host port. We have 2. Is that an issue? We'll see later. But this design first supports MIDI offloading. So all the data flowing through my sensor does not have to go through the CPU. That's very good. Then data from network socket 1 to port 1 can flow, and from network socket 2 to port 2 can also flow. But there is no, I say, cross communication. So data from network socket 1 cannot go to port 2. This is an issue we'll see later on. So again, how is the driver designed? The driver is pretty straightforward. It just connects these host ports to the network sockets. It does all the SPI communication, and that's it. So it's pretty elegant, I would say. But is it enough? We'll see later in a real system. So when I put this driver on an evaluation board, I see one issue. If I want to communicate with my sensor, I need an IP address A on the port 1 and an IP address B on port 2. So this means depending on from which side I connect to my sensor, I need a different IP address. And I think this is very difficult because multiple IP addresses is very, very annoying. So how did we solve this challenge? First, we realized, okay, we are now in the Zephyr world, and I connected directly to the developer of the driver. He told us, yeah, he tried this and that, and he was very open to also help us to improve the thing. Then we also connected to analog devices because they are the chip vendor, and we thought, they may also help us. Now, or at the moment, we are extending the driver together with analog devices that people in future will be able to use it. And of course, we plan to push to the Zephyr project. But what exactly are we changing? I said before, it would be very elegant to have a single IP address. So here we looked how is Linux, for example, solving this issue. And we realized in Linux, there is a switch topology logic that always has a single switch port with a single IP address. This is exactly drawn here. So on top, we have our sensor data communication that is connected to an Ethernet IP socket with a single IP address, which is then going to my virtual switch port. And then integrated in the driver, I will have a small filtering database. So if a packet, an IP packet is coming inside my driver, the driver will remember on which port it was coming in, and therefore it will also answer back on that very port. So I don't need any more 2 IP addresses. This part will be integrated by analog devices together with us. The second part is the time synchronization. We at the ZHW are, I would say, expert in time synchronization. We wrote our complete stack in IEEE 802.1 AS. Usually this runs on Linux, but we also ported that on small Cortex M4 devices, and it runs easily. But we need to implement or to add here the hardware timestamping capabilities to the driver. This portion is already supported by the chip, but it was not in the driver. So here we added quite a lot of code into the driver that people in future will be able to use it as well. The whole design of the driver system should then look like this. So putting these 2 parts together, and for our customer, it should look like this in the end. So we would like to have our host CPU, maybe a Cortex M0 or Cortex M4. We would like to have this time synchronization part that we can trigger measurements exactly on time with sub-microsecond accuracy. We would like to have a single IP address for communication. We would like to have an internal switch chip or forwarding unit that we can put these sensors in a daisy chain, and we don't have all the traffic on our CPU so that it's still all low powered. And of course, it should be on Zephyr. So thank you very much. This was my presentation about how to look on a challenge, bringing it into the Zephyr world, and also maybe take the long run, not just try to make it work on user space, also look into the driver, think about how to improve the driver, talk also to the vendors of the chip, because somebody has to maintain the driver on the long term. And I mean, I don't want to maintain this driver for many, many years, but I think the silicon vendor here, Analog Devices, wants to have this driver in the long run. So if there is now any question, you can ask me now or later on